Welcome back to Mining of Massive Datasets. We're continuing our discussion of recommender systems. In the previous lecture, we looked at content-based approaches to building recommender systems. In this lecture, we're going to look at another popular approach called collaborative filtering. The basic idea behind collaborative filtering is very simple. Suppose we have a user X to whom we want to make recommendations. What we're going to do is we're going to find a group of other users whose likes and dislikes are similar to user X. For example, suppose you're doing movie recommendations. Now, this group of users like the same movies that X likes and dislike the same movies that X dislikes. We call this set of users the neighborhood of user X. Once we find this set N of users, or the neighborhood of users similar to user X, we find other movies that are liked by a lot of users in this set N and recommend those items to the user X. So that's the basic idea behind collaborative filtering. The key trick is to find the set of users that are similar to user X, the neighborhood of user X. And to do that, we need to define a notion of similarity between users. Let's see how to do this. So here's a simple example with 4 users, A, B, C, and D, and a bunch of movies. Okay, HP1 stands for Harry Potter 1, HP2 stands for Harry Potter 2, and so on. And you can imagine whatever names you want for the other movies. SW stands for Star Wars. So, for example, user A has rated 3 movies, Harry Potter 1, Twilight, and Star Wars 1. And he's given the ratings 4, 5, and 1 to these movies. Imagine we are rating on a scale from 0 to 5 stars here. And user B has rated 3 movies, user C has rated 3 movies, and user D has just rated 2 movies. Let's call the set of ratings for a user the user's rating vector. For example, user A's rating vector is what I've highlighted here. Now, if you have 2 users, X and Y, with rating vectors Rx and Ry, what we really need is a similarity matrix, sim of X, Y, that looks at their rating vectors Rx and Ry. Now, the interesting thing here is that there's lots of movies that A has not rated and lots of movies that B has not rated. So the key in defining the similarity function is how we deal with these unknown values. Now, once we define the rating vector, we'd like to define it in a way such that it captures a very simple intuition. It captures the intuition that users with similar tastes have higher similarity than users with dissimilar tastes. For example, in this case, notice that A and B have rated only one movie in common, Harry Potter 1. However, they both rated the movie fairly highly. Whereas users A and C have actually rated 2 movies in common, Twilight and Star Wars 1, but their ratings are very dissimilar. A seems to like Twilight, while C doesn't like it, while A hates Star Wars 1, while C loves it. So we'd like to, it seems intuitively that users A and C are dissimilar, while users A and B are similar. And so we'd like to capture this intuition when we define the notion of similarity. We'd like the similarity of A-B to be higher than the similarity of A-C. Let's see how to do this. So the first option that we try is Jacquard similarity, which we are familiar with from previous lectures. So just as a reminder, the Jacquard similarity of A-B is just RA intersection RB divided by RA union RB. Right? We just take the intersection of the rating vectors and divide it by their union. And notice that the Jacquard similarity is nothing but 1 minus the Jacquard distance of RA and RB. Right? So when we use the Jacquard similarity, notice that A and B have 1 rating in common, Harry Potter 1, and they've rated overall 5 movies, and therefore the similarity of A and B is 1 over 5. And similarly, the similarity of A and C, since they've rated 2 movies in common, is 2 over 4. Notice, though, that when we compute similarities in this way, the Jacquard similarity of AB is actually less than the Jacquard similarity of A and C. This is counter to the intuition that we wanted to capture, that A and B are actually more similar than A and C. So we'll have to abandon this notion of using Jacquard similarities. The problem with Jacquard similarity that we'd like to fix is that it ignores the rating values. It just notices that A and B have watched 1 movie in common, while A and C have watched 2 movies in common, but it doesn't capture the fact that it doesn't take into account how they actually like the movies that they watched. Now, a way of capturing the rating values and using them to compute similarity is to notice that A and B and A and C are vectors, and so we can compute the cosine between the vectors and use cosine distance. And this is very similar to the way we used cosine distances in the case of content-based filtering. So we have let's say we define the similarity of AB to be just the cosine of the angle between the rating vectors RA and RB, right? And let's compute in this case compute the similarity of A and B. And notice to compute the cosine similarity, we have to insert some value for the unknown ratings. And the simplest thing to do is to treat them as zeros, right? Suppose we treat all these unknown values here as zeros. And compute the cosine of the angle between A and B. And when you do that, the cosine turns out to be 0.38. And similarly, when you compute the cosine of A and C, the angle turns out to be 0.32. And notice, in fact, that this captures the fact that the similarity of AB is actually greater than the similarity of AC as we actually wanted. But actually, it's not by much. The similarities are actually very close to each other. It just so happens that the similarity of AB is actually marginally greater than the similarity of AC, which we wanted. Although this still doesn't seem to capture that A and B are much more similar to each other than A and C are. The problem we have with cosine similarities is that it treats the missing ratings actually as negative ratings. What we've done is that we've used 0 to fill in the blanks. And in our rating scale from 0 to 5, 0 is the worst possible rating. So we've sort of assumed that if A has not rated Harry Potter 2, he'd give Harry Potter 2 a rating of 0, which is actually a bad assumption, given that the fact that he actually liked Harry Potter 1. So this is the problem that we have with cosine ratings that we'd like to fix. One way of fixing cosine similarity to accomplish what we want is to use something called the centered cosine. And the way we're going to do that is we're going to normalize ratings for a given user by subtracting the row mean or the average rating of the user. To illustrate what I mean, let's go back to our example. Here are the ratings for the rating vector for A. And notice that the average rating for A is 10 over 3 because there are A has rated 3 items and the sum of those ratings is 10. So the average rating of A is 10 over 3. And similarly, the average rating of B is 14 over 3, and so on. What we're going to do is we're going to go through the row for a user A, and we're going to subtract the row mean, which is 10 over 3, from each of the ratings, except the 0 ratings, which are going to, except the blank ratings, which are going to treat as zeros. Okay? And when I do that, here's a modified rating matrix that we end up with. Notice that A's rating for Harry Potter 1, which was 4, has now become 2 over 3 because we ended up subtracting the row average, which is 10 over 3, from each of the ratings. And 5 has become 5 over 3. And the rating 1 for Star Wars has actually become a negative rating, negative 7 over 3. Right? And of course, we treat the blank values as zeros. Notice something interesting here. If you sum up the ratings in any row, you're going to get 0. What we've actually done is that we've centered the ratings of each user around 0. So 0 becomes the average rating for every user. And positive ratings indicate that the user liked a movie more than average, and negative ratings indicate that the user liked the movie less than average. And the magnitude of the ratings also means, shows how much he liked or disliked a specific item. Now, once we've done this centering, and we can compute cosines using these centered ratings. And when we do that, the similarity of A and B now becomes the cosine of the centered rating vectors RA and RB, and that turns out to be 0.09. And the similarity of A and C using the centered cosine vectors actually turns out to be negative 0.56, which actually captures the fact that A and C are quite dissimilar users. The movies that A likes, C doesn't like, and the movies that A doesn't like, C actually likes. And notice also there's a big gap now between the similarity of AB and the similarity of AC, which shows that A and B are much more alike than A and C are. And in fact, A and C are very unlike each other. So the centered cosine captures our intuition of similar users much better than the simple cosine. And this is because the missing ratings, instead of being treated as negative ratings, are actually treated as average ratings. And also, this turns out to be a nice way to handle tough raters and easy raters, because some people tend to be tough raters and tend to rate movies on a scale really of 0 to 3, while others tend to be easy raters and tend to be much more liberal with their star ratings. By subtracting out the average rating of each user, we've centered users around an average of 0, and we sort of normalized to some extent the tough raters and the easy raters. And so the centered cosine has these two advantages of centering around 0 and capturing our intuition better. Now, it turns out there's another name for the centered cosine similarity in the world of statistics. It's also known as the Pearson correlation. So if you hear somebody talk about the Pearson correlation, they're just talking about centered cosine similarity. Great, now we've come up with a way of estimating similarity between users. Once we have this, how do we actually make rating predictions for a user? So here's a problem. Let's suppose Rx is the vector of user X's ratings. And what we're going to do is we're going to use the notion of centered cosine similarity to find a set N of users, which we'll call the neighborhood. And the neighborhood consists of k users who are most similar to X. We're going to go through the set of all users, compute the similarity between user X and every other user, and select the select k users with the highest similarity values and call that the set N. But we also have to be careful, since we are trying to estimate the rating of item I by the user X. We want to make sure that this set N consists only of users who have actually rated item I. Right? So N is actually therefore the set of users, k users, most similar to X, who also happen to have rated item I. Now, once we have this, we can make a prediction for user X and item I. The simplest prediction is to just take the average ratings from the neighborhood. Remember, the set N consists of users who have also rated item I and are similar to user X. So the simplest estimate is to just use the average rating of all the users for item I in the neighborhood, and take that as our estimate of the rating for user X and item I. Now, the option 1 is very, very simple, but it actually ignores the actual similarity values between users. Now, while the neighborhood N consists of users who are similar to item I, there might be a range of similarity values within the neighborhood. It might contain users who are very highly similar to the user X, and a few users who are not that similar to user X. And so what we really like to do is to weight the average rating by the similarity values. And that gives us option 2. Option 2 is a weighted average. We look at the neighborhood N, and for each user Y in the neighborhood N, we weight Y's rating for I by the similarity of X and Y, and then we just normalize it by taking the sum of the similarities. And that gives us a rating estimate for user X and item I. And notice here that I've just used a shorthand. SXY is just a similarity of user X and user Y. Now, the technique that we've used so far is called user-to-user collaborative filtering, because given a user, we try to find other users that are similar to that user and use the ratings of those users to predict the ratings of the user that we started out with. A dual approach to user-to-user collaborative filtering is item-to-item collaborative filtering. The basic idea is simple. Instead of starting out with a user and finding similar user, we're going to start out with an item I and find similar items to item I. And then we're going to estimate the rating for item I based on the ratings for other similar items. And we can use, in fact, the same similarity metrics and prediction functions as in the user-user model. We can use the centered cosine distance to find, or the centered cosine similarity to find a neighborhood of items similar to our item I. And then we can use the prediction, the average or the weighted average prediction model from the previous slide to actually make rating predictions for the item. And when we do that, here's what the rating function looks like. What we're trying to do is that we're going to predict the rating for user X and item I. So we're going to start with the item I, and we're going to find a neighborhood of items. The neighborhood of items, NIX, is just a set of items that are rated by that are both rated by the user X and are similar to the item I that we're looking at, right? So we just take the item I, compute the similarity between item I and every other item in the set that we know about, restrict our attention only to the items that have been rated by the user X, and then take the top k of those as a neighborhood NIX. And once we do that, we can just use this same weighted average formula that we had from the previous slide to predict the rating of user X and item I. So let's work through an example to illustrate what this means. Let's say that the neighborhood size that we want to pick, the size of n, is actually 2. We're going to be looking at the 2 nearest neighbors of item I, and we're going to be using item-to-item collaborative filtering. Here's a utility matrix, here the yellows are the known ratings in the utility matrix. We have movies on the y-axis, and we have users on the x-axis, and the blanks are the unknown ratings that we are trying to predict. And let's assume that the rating values are between 1 and 5. Remember, our first step, and let's say our goal is to estimate the rating of movie 1 by user 5. Remember, the first step is to take movie 1 and find other movies that are similar to movie 1. We're going to use Pearson correlation as our similarity, which is same as the centered cosine distance that we computed. So we're going to take every other movie and we're going to compute its centered cosine distance from movie 1. And when we do that, movie 1 is, of course, the centered cosine is 1.0. Movie 2 is somewhat dissimilar to movie 1, and so on. And so this vector here illustrates the centered, lists the centered cosine distances of all the different movies with respect to movie 1. And what we're going to do, remember, since our neighborhood size is 2, we need to find the 2 movies with the highest similarity to movie 1, and that have also been rated by user 5. And those 2 happen to be movie 3 with a similarity of 0.41 and movie 6 with a similarity of 0.59. So we're going to pick those 2 movies as our neighborhood for movie 5, or for movie 1. Once we do that, the similarity values are, in this case, 0.41 and 0.59, and we're just going to use a weighted average estimate to predict the rating for movie 1 and user 5. And the weighted average is just 0.41 times the rating of movie 3, and 0.59 times the rating of movie 6, which is 3, and then divided by the normalizing value, and this gives us 2.6. And 2.6 is our predicted rating for user 1 and movie for movie 1 and user 5. We've looked at 2 ways of doing collaborative filtering: user to user and item to item. Now, in theory, user to user and item to item are dual approaches and should have similar kind of performance. Now, in practice, though, they don't perform similarly at all. In fact, in practice, it's been observed that item-to-item collaborative filtering hugely outperforms user-to-user collaborative filtering for most use cases. Use cases, for example, such as movies or books and so on, item-to-item clearly outperforms user-to-user. Now, we might wonder why this is the case. And the answer turns out to be quite interesting. Items are inherently simpler than users. Items belong to, for example, a small set of genres. For example, you can take a piece of music and classify it as classical music or pop or rock and so on, whereas users tend to have very, very varied tastes. So the same user might like, for example, Baroque classical music and acid rock. And these two are very different genres, but the same user might actually like both these genres. But it's very rare that an item would actually belong to both these genres of music. And therefore, it turns out that the notion of item similarity is inherently more meaningful than the notion of user similarity. And that's why item-to-item collaborative filtering works much better than user-to-user collaborative filtering for most use cases.